Hello again everyone. When the experiment I will tell you about the energy in magnets, which is a very difficult subject, is done by you will see that your doubts are unfounded. Let me first try to summarize what we will do so that it can be shaped in your mind without going into narratives. With the help of a switch, we will provide current to a large coil winding for a short time. Meanwhile, the coil winding will start to attract the magnet, which can swing like a pendulum at the end of the rope opposite it, and immediately after the magnet touches the coil winding, we will turn off the switch and cut off the current. We will measure the electrical energy we consume until the moment of contact and the energy lost due to heat in the coil separately with the help of an oscilloscope. The front contact surface of the magnet attached to the wire, which we fixed as a continuation of the wire coming from a different mini coil winding that we will place in the main coil winding, and the stretched flux wire acting as a key placed 1 centimeters before the contact border. We can observe the start time of the additional peak wave that occurs when they touch each other and the change in direction of the waves at the moment of contact on the oscilloscope. We will be able to see and calculate the speed of our magnet at the moment of last contact and the kinetic energy we obtained. Finally, we will be able to compare the total energy gained versus expended and see whether there is any magnetic energy gained from the extra permanent magnet. Now let's move on to the details of the experiment. We adjusted the coil winding amount to a resistance value of 1 ohm, which will not be too low, and the same as the shunt resistor value we will use. I used a 12-volt 9-amp battery to reduce electrical noise. When starting the experiment, we turn on the switch connected to the extended cable end and start the current. We can now see this point, the moment of contact, on the oscilloscope, where the innovation does not increase in the same direction, but begins to move in parallel. On the line along the path of the magnet touching the coil winding, we come up with a conductive wire parallel to the coil winding, with a distance of 1 centimeter from the contact point, and corresponding to the midpoint of the magnet while it is touching. We place another conductive rod connected to the main circuit. We stretch it by wrapping it from top to bottom and touch it to the other wire. When the magnet touches the horizontally stretched wire, it moves away from the vertically stretched wire and is disabled. We place the mini coil winding, consisting of 15-20 turns of very thin coil wire connected serially to this second wire, which will complete the switch function, into our main large coil winding. We can ensure the connection by stripping the wire end coming from the mini coil winding and attaching it to the underside or back of the magnet, or by a similar method. Before proceeding with the experiment, it is necessary to pay attention to some details. The purpose of doing the control experiment is to observe whether the energy gained without permanent magnet movement is not more than the supplied electrical energy before the actual experiment, and to see whether the experimental setup and resistance values are set correctly. The settings and circuit connection of the oscilloscope will be exactly the same as in the actual experiment we will do shortly. We connect the oscilloscope as in the display circuit in the figure. We turn the switch on and off for a time that would not be much different from the permanent magnet movement time in the actual experiment we will do shortly. Waves appeared on the oscilloscope screen after the moment of contact. We put it in between and tighten it to prevent the magnet from moving, and then we turn the switch on and off. Now let's look at the electrical energy consumed in the oscilloscope we have adjusted. In this selection we find the value 3.96. Now let's move on to the second mathematical operation on the same waves to find the gained energy or the released coil heat energy. The only difference in this calculation is to change FXB as first channel so that the current wave multiplies with the current wave, not with the voltage. When I selected channel 1 instead of channel 2, the 3.96 value did not change. Thus, we saw that our experimental setup worked correctly, or that there was no mistake that would change the result. Now let's move on to our actual experiment. We start the current by turning on our main switch,
S1.
As the magnet rapidly approaches the coil winding, first 1 centimeter left, the front face of the magnet and the switch will touch one of the tensioned ones in
S2 position.
completing the circuit for a short time, and a peak wave will occur with the activation of the inner mini additional coil winding. When the magnet moves a little further, the 2 wires will be disconnected and the mini coil will be deactivated, and thus the moment of contact can be observed more clearly. We quickly opened the switch and closed it when the magnet touched the coil winding and waves were formed like this. With such calculations, we find the electrical energy spent for the coil winding as 4.18 joules, and the energy spent for coil heat losses without changing the starting and ending points of the cursor as 3.58 joules. First, we started the integral operation. We opened our cursor. We reduced the unit duration of the wave and determined the beginning and ending location from the integral mathematical function. After moving the cursor to the touch point, we selected the mat part, that is, the integral result, as the unit to be measured with the cursor. By multiplying channel 1 and channel 2 with these adjustments, we found the value of 4.18 joules. So our total energy spent is 4.18 joules. When we multiply channel 1 and channel 1 again, we found the value 3.58. So we found the value of 3.58 for coil heat losses. Now let's calculate the final speed and kinetic energy of the permanent magnet when it touches the coil winding. As can be seen, we see an upward peak or group of waves to the left of the wave that disrupts the normal slope. This peak wave starting point shows the distance 1 centimeter from the permanent magnet to our actual coil winding. As we can see more clearly in the wave showing the current, the first moment when the wave starts to move parallel while traveling downwards is the moment when the magnet touches the coil winding. With these adjustments, we found that the time difference between the two cursors was 9.64 milliseconds. And when we divided the distance taken by time formula x divided by t, that is 1 centimeter, by this time we calculated that velocity was 1.03 meters per second. When we measure the mass of the magnet with a digital precision scale in order to find the gained kinetic energy from the formula 12mv square, we find the value of 1.44 kilograms. When you substitute it into the formula, it equals 102 times 1.44 times 1.03 squared. We find the value of 0.76. In order to find the potential energy gained by the magnet rising upwards due to the movement of the pendulum, we find that the amount of rise is 20 to the 14 equals 6 millimeters. When we substituted the values in formula, we found a value of 0.08 joule. Now let's find our total energy gained. 3.58 plus 0.76 plus 0.08 equals 4.42 joules. When we subtracted it, we saw the existence of an energy of 0.24 joules, as it was shown on the table with the experiment. The only source of additional magnetic energy released is the pathways that provide the magnetic attraction force in the magnet. I invite everyone to work together to repeat the experiments together and move electrical, motor and other studies to the next level.